Okay, let's review how the standard convolution works. So if you remember, in the case of an RGB image, so red, green, and blue image, in this case we have a 6 by 6 pixels by 6 pixels and 3 channels, the red, green, and blue. And we want to filter with a set of filters, or a filter with which has a number of channels 3, just like the input image. And the size of this filter is a 3 by 3. We're going to perform just a stride of 1, meaning that we're going to move our kernel just by 1 step. And we are not going to have any padding, so we're not going to have any zeros in here. And as you can see here, because we're not going to have any zeros, we're going to end up with a 4 by 4 output image. And then the way we did it, if you remember, we took this red one, we convolve with the red one, with red filter, or pink filter with the red filter, plus this light green filter with the convolved with the dark green filter, plus the light blue filter by the dark blue filter. And then and this would give you a 2 here. And then because the stride is 1, so you move the filter and you perform your convolution again until you get your output image. So in this case, we're going to look at the case where we have multiple filters, which will result in a number of multiple outputs as well. So let's assume that we have our 6 by 6 by 3 input image, 3 meaning RGB, and we have a number of filters. So in this case, we have 2 filters. For example, this one would detect, goes from -1 to 1, so it's going to detect the vertical edges. Let's say this one here is going to detect the horizontal edges. And so just like what we've seen before, you convolve this one or the input image with the first filter, you get the first output. You convolve the second, your input image with the second filter to get the horizontal edges. You get this output image. And this would give you a number of output, multiple outputs. In this case, again, because you have you have no padding, so you'll end up with a 4 by 4. And in this case, because you have 2 filters, you end up with 2 outputs. Now let's illustrate this in the case of multiple filters. Let's say we have a number of filters. So this is our input image for the first channel, red, green, second channel, third channel, and we have, in this case, a number of filters for channel 1, channel 2, channel 3. So we perform our convolution with the first filter. Now we have filter K1. We do the same thing. We perform convolution. We get the second output. We do it with the third filter, K2. We do the same operation. We end up with a third output and so on, okay? Depending on the number of filters. So for example, K0 was detecting the vertical edges, K1 was detecting the horizontal edges, and so on. So depending on the number. Now, that's just the standard, that was just a standard convolution. Now there are other types of convolutions which have shown some success in certain applications. So for example, in the case of the unshared convolution, in this case, the local connections like so the local connections like convolution, but no sharing. So this is similar to the normal convolution, but you don't share the the filters. Meaning, so if you take this here, you are going to this region of the image, you're going to convolve it with the first kernel, kernel 0, to get this output. Now, this, when you do a stride, when you move your window one step, you're going to convolve it with a different filter. So you don't share. There's no parameter sharing just like before. And then this will give you the second output pixel. And then when you move again your window by one step, but by one stride, you convolve it not with the first with the K1 filter, but another filter, K2 filter. And then you get your output pixel. And the same thing, this is convolved when you move again by one stride, you have a convolution with another filter, K3. You get the output pixel, you do the same thing. And this is with kernel 5, this is with kernel 6, kernel 7, kernel 8, and kernel 8, okay? So in this case, you need 9 kernels to perform or to get your output image. Now this shared convolution has been used in deep face, if I am correct. I think, as far as I remember, it has been used for deep face. So deep face has been developed by Facebook for face recognition. And that's why it's called deep for deep learning, and face for probably for the face and the Facebook as well. And the idea is they used a large number of faces from the subscribers, and they used them to train a network using Unshared convolution. Another type of convolution is the tiled convolution, which is a compromise between a standard convolution and the unshared convolution, or what sometimes also called locally connected convolution. So in this case, you, instead of having a number, a large number of filters, you just have a set of filters. For example, in this case, we just have 2 filters, K0 and K1. And we cycle between these shared parameter groups. So meaning that, so we have our 2 filters, K0, K1. So for this pixel, for this region here, we filter with K0. We get our output pixel, and then we move our window by one stride. But then in this case, we convolved with the second filter, K1. We get our output pixel. We move again to, or because we're cycling, we move to the K0 filter. We get the output pixel, and then we move again to filter K1, and we keep tiling. We keep jumping from one filter to another. Now this, you can look at this reference for the tiled convolutions if you want to find out more. But then when you compare the unshared convolution, the tiled convolution and the standard convolution, as you can see here, for the traditional convolution, you have, there is only one kernel and it is applied everywhere. So this is your kernel. It has the weight A and B. You apply it for this to get this output, okay? And then the output of this, you can call it hidden node. You convolve your input. You convolve your input with this, you use this input, and so you have parameter A and B. Same thing here, A and B, A and B. But then in the case of the tiled convolution, for the case of t equal 2, so for this you get A and B, and then you jump to C and D, and then you go back to A and B, and then you jump to C and D. So this is with t equals 2. And then you can see here that the traditional convolution is just like the tiled convolution, but with t equal 1, okay? So you don't jump from one filter to another, your t equal to 1. as opposed to the case of unshared convolution, where there is no sharing at all. So for this, you have A and B. And for this output, you have C and D. For this one, you have E and F. For this one, you have G and H, and so on. So there are no shared connections. And this has, of course, an impact on the computational time, but also it has an impact on the performance. And depending on the application, as we've seen in the case of deepfake, sometimes you get better performance. Okay, thank you.